All right, so the next thing we're looking at with limits is this idea of indeterminate forms. Now, what I mean by an indeterminate form is if we try and use direct substitution, like we were looking at in the previous video, we're going to come out with 0 divided by 0. Okay, now in that situation, you really don't know what the limit is equal to because that is indeterminate. You can't figure it out from that. So what we're going to have to do is take our function and simplify it down, which typically is going to involve factoring, canceling a common factor, and simplifying. Now, what this up here is telling us that if we're able to take our original function and simplify it down, then the limit of our original function is equal to the limit of that simplified function. Okay, so let's go ahead and let's take a look at this first example. Okay. Now, the first thing that you would see here is if we try and use direct substitution. So let's try it. We'll try direct substitution. Okay. Well, we're looking at the limit as x approaches 1 of x cubed minus 1 all over the quantity x minus 1. So we would have 1 cubed minus 1 divided by 1 minus 1, which gives us 0 over 0. This is what I was just saying is considered indeterminate. Okay, all that basically means is there's more work that we have to do to figure out what our limit is. Okay, so now our next step is going to be take this function that we're given and see if we can try and simplify it somehow. I'm going to take my x cubed minus 1 all over x minus 1, and I'm going to try and factor out that numerator. Now you might recognize that this is a difference of cubes, so remember your difference of cubes formula. This would factor as x minus 1, and then times x squared plus x plus 1. Okay. In case you don't remember your difference of cubes, let me just go ahead over here on the side. We have a cubed minus b cubed is always equal to a minus b times a squared plus ab plus b squared. These are difference of cubes formula. All right, and we still just have that x minus 1 on the bottom. Well, of course, you'll notice we have a common factor now, x minus 1, which we can just go ahead and cancel out on the top and the bottom, which leaves us with x squared plus x plus 1. All right, now if we go back up to our original problem then, because we were able to simplify this down, what that theorem above was telling us is that the limit of our original function is now equal to the limit of our simplified function. So our original problem is now equal to the limit as x approaches 1 of this simplified function, x squared plus x plus 1. Now the nice thing here is once you're able to simplify it down, you can just use direct substitution. So if we plug 1 in, 1 squared plus 1 just equals 3. And that's our answer. Okay, so if you get an indeterminate form, so 0 divided by 0, when you first try and plug it in, then simplify your function and use that simplified function then to find your limit. Go ahead and look at another one. All right, so again, if we were to try direct substitution, looking at the limit as x approaches 1, let's see what happens when we plug this in. We have 2 times 1 squared plus 1 minus 3 all over 1 squared minus 1. Right, but again, we get 0 over 0, which is indeterminate. We're going to have to try and simplify. All right, so let's take our function, 2x squared plus x minus 3, all over the quantity x squared minus 1. Let's go ahead and factor out both the top and the bottom on this one. All right, so our numerator, we have a 2x squared. It's going to be a 2x and an x. We have a 3 on the end, so it's got to be a 3 and a 1. And to get the positive in the middle, it's going to have to be a plus and a minus. And then our denominator is just a difference of squares, so x plus 1 and x minus 1. And once again, we'll see we have a common factor that cancels out. And we can just simplify this down to 2x plus 3 all over the quantity x plus 1. All right, so now our original limit is equal to the limit as x approaches 1 of this now simplified function, 2x plus 3 over x plus 1. And then we can just use direct substitution. So 2 times 1 plus 3 all over 1 plus 1, which will just give us 5 over 2. All right, let's try another example. All right, so this time we're looking at the limit as x approaches 4 of this rational function. Same as the others, if we tried to just plug 4 in using direct substitution, we would see that it's indeterminate. Skip that part this time just because I think you guys can do that piece on your own. I'm going to go ahead and go straight to the simplifying part. So just like the others, we're going to want to factor out our denominator this time. And this one's just a quadratic. You can go ahead and factor this as x minus 4 times x plus 1. And of course, the x minus 4 is going to be our common factor that we can cancel, which leaves us with 1 over the quantity x plus 1. All right, so our limit that we were originally given is equal to the limit as x approaches 4 of 1 over the quantity x plus 1. Just use direct substitution. Plug 4 in for x, and we get 1/5. All right, one last one like this. Let's go ahead and look at the limit as x approaches 0 of this function. Once again, if you plugged 0 in, you would see that it's 0 over 0, which is indeterminate. So we're going to have to again simplify this function. All right, so this time our numerator, we can go ahead and just factor an x out of everything, which of course gives us a common factor that we can cancel on the top and the bottom. So this just simplifies down to x squared plus x plus 1. All right, so our original limit then is equal to the limit as x approaches 0 of x squared plus x plus 1. So using direct substitution, plug that 0 in, and it equals 1. All right, so this is using direct substitution after you've simplified a function down that's in that indeterminate form where you have a 0 over 0. All right, now these next two examples, these are also going to be indeterminate, but instead of just a straight rational function, we have something with a square root in it. Now what we're going to have to do with these is rationalize. Typically when we talk about rationalizing something, we're rationalizing a denominator. In this case, it could be the numerator, it could be the denominator, but we're still going to use that same idea of rationalizing by multiplying by a conjugate. Now, just for the sake of doing it, let's again just make sure that this is indeterminate. So we're going to first try direct substitution. So if we're looking at the limit as x approaches 3, we'd start by plugging 3 into here. But of course, square root of 4 would be 2. 2 minus 2 on top is 0. and a 2 on the bottom, so this is indeterminate. All right, let's go ahead and try to simplify this. So we're starting out with our original function, square root of x plus 1 minus 2 all over x minus 3. All right, now what we're going to be trying to do here is rationalizing. So in order to rationalize something like this, we need to multiply by the conjugate. Since the square root's on top, we're going to multiply by the conjugate of the numerator. Remember, conjugate just means that we're changing the sign in the middle. So since it was a minus to begin with, we're going to change it to a plus. We're just going to multiply by that same thing on the top and bottom. So we're really just multiplying by 1. We're not changing the value of anything. All right. So if we were to FOIL this out then, square root of x plus 1 times the square root of x plus 1 is just equal to x plus 1. Of course, since they're conjugates, the middle terms just cancel, and then on the end, negative 2 times 2, this gives us minus 4. I'm not going to FOIL out the denominator, I'm just going to leave it in factored form. All right, now you'll see our numerator just simplifies to x minus 3. And this is why I chose to just leave that denominator in factored form. It's always going to work out this way, that you'll have something that cancels out. In this case, the x minus 3's are going to cancel out. And we're finally just left with 1 divided by the square root of x plus 1 plus 2. All right, so back up here, our limit as x approaches 3 of our original function is now equal to the limit as x approaches 3 of our simplified function. So 1 divided by the square root of x plus 1 plus 2, and then we just use direct substitution. So 1 divided by the square root of 3 plus 1 plus 2. All right, so that is just going to be 1 over 4. And that's our answer. All right, so when you get an indeterminate form, when you're dealing with something with a radical in it, you're going to rationalize either the numerator or denominator to simplify your function. Let's go ahead and look at one more of these. I'm going to skip over it, but again, if you were to try direct substitution right from the beginning, you would get 0 over 0, which is indeterminate. I'm just going to jump straight to simplifying. All right, so once again, our radicals are in the numerator. So we're going to rationalize by multiplying by the conjugate of the numerator, which puts a plus in the middle instead of a minus. Make sure you multiply by that same thing on both the top and at the bottom, but you're not changing the value of the expression at all. All right, I'm going to FOIL at the top. So square root of 2 plus x times square root of 2 plus x is just 2 plus x. Our middle terms cancel out, and then square root of 2 times square root of 2 is just 2, so minus 2. And the denominator, I'm going to leave it factored. All right, so this is going to simplify down to x divided by x times that conjugate. Of course, you'll see that the x's on top and bottom just cancel out, and we're left with 1 divided by the square root of 2 plus x plus the square root of 2. All right, so our original limit then is equal to the limit as x approaches 0 of this new simplified function. And then we can just use direct substitution again. Go ahead and plug 0 in for your x's. You just get 1 over, this would be square root of 2 plus another square root of 2, so 2 square root of 2. And if we were to rationalize our denominator, we get the square root of 2 over 4. All right, that's it for our indeterminate forms.